Well, it is a pleasure to welcome you all to Waterloo, and I hope you have an enjoyable meeting. I'm very honored to give you the first talk, and from the people that I see, I'm afraid I will bore a lot of you because most of what I'm saying is known by everybody that has been involved in Bayesian analysis. And I'm using obsolete technology, but Philip kindly gave me some piece of modern technology. And the reason why I do this is because I think it is easier to absorb material if I leave the transparency a long time there and talk about it, rather than flip the PowerPoint back. Anyhow, I called the talk a gentle introduction because I will not talk about too many technical details. That's for later. You will have plenty in the next tutorial and others. What I would like to do is to sort of show you the basic concept and the basic difference between statistical analysis of data and probabilistic analysis of data the Bayesian way. And then give you some examples that I've taken from my work over the past many years in application to medicine. And what I found in the studies, usually clinical trials and so on, and interacting with the doctors, is that it is appalling the kind of conclusions that they draw because they use classical orthodox statistics. And I will give you some examples later. Before we go on, I want just to give you two basic references to introductory material. And the first one is by Professor Celia with contributions from Professor Skilling. And it's the nicest tutorial book of introduction, which actually is not just tutorial. There is a lot of interesting things, especially the last couple of chapters in the second edition by Professor Skilling. So if you don't have that book, I suggest you grab it. The other one is by Professor Skilling, and I'm not just want to please him because he's the chair. I find that paper that was published in Journal of Microscopy is actually one of the best as a guide and introduction to what Bayesian probabilistic analysis of data is. And although it is succinct, I think it's a must reading. I underline the word probabilistic because if you take any of the normal statistical analysis of data that is done all over the place, it has been done for 150 years, they use the word statistical. But Professor Skilling pointed out that it's probabilistic analysis of data. The reason is very simple. As you probably know, in Bayesian there is no statistics. There is probability theory. And that is something that actually I would like to invite you to think about it, because when you read Bayesian analysis of data, a lot of people stick in the word statistical. So you have expressions like Bayesian statistics, and that's a sort of nonsense, because let's see why one should use probability rather than statistics. If you remember, the difference in the two approaches is the way one defines probability. If you are a Bayesian, then you believe that probability gives you a representation, a measure, so to speak, of the degree of belief in the truth of a proposition. Instead of degree of belief, you can call it plausibility. On the other hand, if you are a classical statistician, you believe that probability is a frequency, long-run frequency, which is obtained by not just looking at your sample, but imagining that you repeat the experiment an infinite number of times, and then in the limit, you will get the frequency, which is the probability. And that is considered to be more objective by these mathematicians than the Bayesian analysis that sort of has degree of belief or plausibility, has a flavor of uncertainty. of subjectivity. And that has been the clash between the two approaches, as you probably know, since the time of Laplace. Since 1842 on, there's been a sort of intellectual war between the two schools. And I think the MaxEnt symposium is one of the few places where Bayesian can collect themselves and sort of encourage each other to keep the good fight on. There's been a way of pointing out to the frequentist that we don't have usually an infinite amount of data. We have just a sample, which normally is a finite number of data. And at the same time, they insisted that the frequency should be, the frequency definition of probability should be applied only to what they call random phenomena. And I challenge you to find on the web or anywhere else a mathematical definition of randomness. Nobody knows what randomness is. We have a sort of intuitive feeling. You know, we have a Bernoulli urn with balls inside. We shake it, and that's supposed to randomize the thing, whatever that means. But the important point is that from the frequencies point of view, you have to have a random variable in order to apply probability theory. That's not true in the Bayesian approach. In the Bayesian approach, probability theory is a measure of the state of knowledge of the researcher. Can it be applied to the truth of any proposition? So there is a big conceptual difference between the two. Naturally, the mathematicians that were espousing the frequency definition of probability, they knew very well that you don't have usually an infinite set of data, and that actually not all quantity of interest in science are actually random variables. The famous example of Laplace that estimated the mass of Saturn was typical of the success of the Bayesian approach. I don't know if you know the story. Laplace estimated, with Bayes' theorem, estimated that the mass of Saturn would be 1 over 3,512 times the mass of the Sun. And he said, he gave odds 11,000 to 1 that this value will not be more than, will be less than 1% from the actual true value. And 150 years of further refinement of the measurement have changed that estimate by Laplace by only 0.6%. So that was a tremendous success, and of course it enraged all the frequentists. Why? Because they said, well, you can't apply probability to the mass of Saturn. The mass of Saturn is a parameter. It's not a random variable. What are you talking about? And the success of Laplace estimate didn't register with them at all. In the approach that the frequentists took, not realizing that not all the quantities that we deal with are random variables and that you have a finite sample, they invented a new subject, statistics. So statistics is not just probability, it's something more. And why they invented it is the reason why you want to make the quantity that you estimate a random variable. So if you take the sample and take some statistic called some quantity that represents some sort of average behavior of the quantity you're interested in from the sample, then since the sample contains experimental measurements, they will be subject to random noise. Therefore, the statistic, a mean, a median, or something else, becomes a random variable, and you apply it. You can apply probability theory to it. Well, this approach essentially has dominated, for the past 150 years at least, has dominated the area of statistical analysis of data. And since I started to work in relation to medical areas and talking to doctors, for instance, doctors are scared usually of mathematics. And so what they do typically in big hospitals, research hospitals, like the two that we work in collaboration with in Toronto, they take the data, they bring it to the section of statisticians that analyze the data. The statisticians will push the right button on the computer and run the appropriate software to do what the statisticians want to do. And then they present graphs, tables, and so on to the doctors, and they present some estimate of how you can trust that result. I'll show you what that is. It's called the p-value usually. And then the doctors believe that they've got the truth. Well, despite the success of Laplace, they still believe that that's the correct way to do it. But let's see, I've piled up some examples of what this method of statistical analysis of data with the frequentist approach has produced. You take clinical trials and you look at the results of the clinical trial, and then you publish a paper about it. And in particular, since we're working on cancer, mathematical oncology, a fancy name, I compiled a few examples of cancer risk that have been found with the classical orthodox statistical approach for cancer. So the first thing you find is that if you use electric razors, your chance of increased cancer of some type is high. But if you have a broken arm, but only if you're a woman, then increases the chance of breast cancer. The thing goes on. Fluorescent lights, stay away from them. Because it's really terrible. Allergies, don't get any allergies because your risk for cancer increases. These are real papers. I'm not making them up. Breeding reindeers, you better stay away from them. But the best is to come. Being a waiter, it's very dangerous. Owning a pet bird, I don't know why, but it's a risk for cancer. If you are too tall, but also if you are too short. I attract your attention there because this, if you read the newspapers, watch television news, and so on, just recently I heard on the radio that, for example, the latest clinical trial about the effect of salt on hypertension. You know, we have been told to stay away from salt because it's dangerous for you, and many people have eliminated salt. And so there was this talk radio show host that started to really get mad. He said, for the past 20 years, I've been told to stay away from salt. I eliminated salt. The food tastes terrible. And now this clinical study says that it doesn't make any difference. I feel cheated. Hot dogs, stay away from them. Increase your risk tremendously. And if you think you are safe, owning a refrigerator will kill you. I mean, you can find more. This is an interesting paper by Stephen Goodman, who is both an MD and a statistician working at Johns Hopkins. And he has written a lot of papers trying to educate the medical professionals about going to the Bayesian analysis. So with not that much success. In fact, there is the best place for Bayesian analysis of medical data is actually Houston, the MD Anderson Cancer Center. And Donald Berry is there, and he has been pushing for applying a Bayesian approach, especially to clinical trials. If you think about it, the way they do clinical trials today, say, suppose you want to test whether a pharmaceutical company will pay you millions to do a clinical trials to test the effectiveness of a drug against a certain disease. And the way the standard orthodox statistical approach is that you have to design the experiment, the clinical trial, and you have to have a fixed duration in collecting data. So suppose that, say, the duration, the latest I've heard about ovarian cancer at the University of Toronto, They had a multi-nation participation, and the duration of the clinical trial was 10 years. Now, suppose that you try this pill, and you have your two groups, the control group and the group affected, then you give the pill to the ones that have ovarian cancer, and you find that this pill is very effective. After 3 years, the rate of increase of the cancer spreading and so on in that group is much less than what you would expect. Well, if you are a classical statistician, you cannot stop the trial. You have to keep going and let these people die, the ones that don't take the pill that is effective, for 10 years. If you are a Bayesian, you can stop it at any time and the data are still useful. But not if you are a classical statistician. If you don't go the whole 10 years, the clinical trial is washed out. I don't want to go into the details why, but that's a fact. And so there are moral, ethical implications about the way doctors use statistical analysis in clinical trials. Well, I asked myself then, when I saw these things, where does this silliness come from? What's going on? Why they are so strange in accepting ridiculous results like that? And if you think about it conceptually, the reason is, for the frequentist versus the Bayesian, is that the frequentists are mathematicians who want to use deduction in order to find conclusions. And so in a scheme which you will find better explained in Professor Silian's Skilling book, essentially the mathematical method used in deduction is the one used in pure mathematics. You start with a set of axioms that you take for true, and then you deduce logically the consequences. So applied to a physical setting, you know what the cause of something is, and then you can predict all the effects depending on the circumstances. And that deduction is rigorous. So you think that now you've got an explanation of your experimental results, which is unassailable and without doubt. This method can be applied even to games of chance, where it's easier to understand. For example, suppose you have a coin. And suppose you know axiom that the coin is fair, it's not biased. Then you can predict anything you want, how many flips you make of the coin, and whether there will come out all heads, they will come out all tails, 9 will be heads and 1 tail, and so on. If you make 10 flips, you can deduce any possible outcome you want. But you have to assume that the axiom you started with, the coin is fair, is correct. I remember years ago, before I retired, I used to teach a classical mechanics undergraduate course to our students in applied mathematics, and there was a pure mathematics students in there, and I was pointing out this, the way science actually works is not by deduction, but by induction, and therefore your scientific conclusions will always be subject to a certain error. And I was pointing out that that's unavoidable, and he said, after class, he said, no, I don't understand why you physicists don't do the axiomatic method. I said, what do you mean? He said, well, assume a set of axioms and then deduce all of physics. He said, how would you do that? What set of axioms would you start with? He said, well, I thought about 2 of them. The first one is, there is stuff. I said, fine, certainly there is stuff. And the second axiom, he said, there are stuff movers. Okay. What was the third axiom? He said, well, I haven't thought about that. It's up to you physicists to keep going. But if you do that, then you can derive rigorously all of physics. That attitude actually is not too far away from a lot of people believing that that's the way science works. But in reality, it works the other way. The mathematical point of view is well illustrated by what mathematicians do to prove statements. I took this from a typical undergraduate text in statistics. And the method of proving something, for instance, is seen very there. You start with an axiom or a proposition that you believe true. So, for example, suppose you want to find out whether there is a largest prime number or there isn't. There are an infinite prime numbers. So you start out by assuming, that's the axiom H, the hypothesis H, that there is a largest prime. Then you reason deductively, logically, by saying, well, if there is a largest prime, then you can arrange them in an increasing order, and the last one will be, say, P sub n. If there is a largest prime, then all the others, largest, will be composite numbers, so they can be divided by one of the Pn's, right? Because there won't be prime, since there is only the highest one, Pn. But if you then take the combination, oh, I can use this. If you take the combination, the product of all these finite set of prime numbers plus 1, this is not divisible by any prime number of the Pn's. And so the result is that then you conclude that if there were a largest prime number, you would end up with a contradiction. Therefore, the hypothesis is wrong. No probability is used here. It's just pure deduction. But now, the frequentists, the statisticians of the classical variety, use that for the probabilistic case. They say, well, suppose that you flip a coin 100 times, and you can't disprove, even if the coin comes out 100 times heads, you cannot prove mathematically, rigorously, that the coin is biased. Why? Because even with a fair coin, in principle, you can get 100 heads in a row. But, they say, the probability of such an extreme result is very small. Therefore, they conclude, the hypothesis is disproved. In other words, the smaller the probability of the extreme result, the evidence mounts that the hypothesis you started with is false. In other words, they compute this probability of observing such an extreme value, okay, under the assumption that the hypothesis is true. That probability comes out very small. It's called the p-value, and arbitrarily they take the point 0.05 as being the boundary between above and below. If that p-value is less than 0.05, the hypothesis is discarded. But notice the curious logic. The way to calculate that p-value is compute the probability of observing such an extreme result under the assumption that the hypothesis is true. So how can you take that as proof that the hypothesis is false? You see the sort of funny logic that they use? And therefore the p-value cannot be trusted. Well, in real science, what we have actually is induction, or plausible reasoning. We have a bunch of data, and we have to make an educated guess about what the cause will be. So in this picture, the flow goes in the reverse. You start with the observation, the experimental results, and you want to find out which plausible causes have produced those results. Naturally, since you start with any of these observations, you can have one cause, another cause, another cause, you can have many. You have to decide how much you trust your conclusion. And the question then becomes, what kind of method do we use to have the best inference of the cause given these results? Let's take a simple example again with coins. If you say you have a coin and you flip it 10 times and you get 7 heads, what is the chance that the coin is biased? Well, a classical frequentist statistician will not be able to answer that question because you don't have a frequency there. The frequency, you can say 7 over 10, 70% is the frequency because the number of data is very small. And remember that the definition of probability as frequency is in the limit as the number of experiments goes to infinity. But with the Bayesian approach, when you apply Bayes' theorem, you can make a guess with that, and then you can find also how much you believe in the result that you got, because you will be able to find also the error bar, so to speak. The question still is, how do we make the best possible inference from the data? And the arguments given by Laplace and his followers weren't as clear-cut as we desire until 1946, when Richard Cox produced a paper that was published in the American Journal of Physics. And I think, you know, the American Journal of Physics is supposed to be a physics journal for advanced undergraduates or graduate students. And it's not supposed to publish, at least the editorial statement that I read in the American Journal of Physics years ago, stated that no new research should be submitted, but only papers that explain the knowledge that we have of physics to undergraduate and graduate students. And I find it remarkable that the editor has been so enlightened to actually allow the MaxEnt symposia to be published there. And there aren't that many journals that want to publish Bayesian analysis of data, probabilistic analysis of data. So it is remarkable, but I think that also shows that Richard Cox must have had trouble publishing his fundamental paper in a more sort of research-oriented journal. Anyhow, the American Journal of Physics, we can thank them for publishing it, because in that paper, we actually laid down the method to make the best inference. You will see more in the coming tutorial by Professor Newton and others. And essentially, I'm now summarizing very, very poorly what he did, and I hope you've all read that paper, or at least a version like in some of the literature. What Cox started by asking is, in science, as I said, we go from the observations to the possible causes, and we make a guess. And we want to find a way to make the best possible guess based on the data. And so, say, consider any proposition, and you ask yourself, what is my belief in the truth of the proposition? For that, you may have some data, but you also have prior knowledge about the foundation, the setup of that particular experiment. So if you take, for example, the proposition, it will rain this afternoon, and you ask, how can I state in probability theory, assign a probability to that statement, for that statement to be true? Clearly, it will depend by a lot of things. Say, suppose I just woke up, I have all the windows closed, and as I woke up, I think, will it rain this afternoon? I don't have any previous knowledge. So I will have to assume that my previous knowledge is sort of uniform ignorance, right? On the other hand, suppose I wake up, get up, open the windows and look at the sky. Now I have more information as background information. So my estimate of what the likelihood of that statement to be true will depend from the fact that now I have more background information. Similarly, if I wake up, open the window, look at the sky, and then switch on the television set and look at the weather channel, now I have even more background information. So my assessment of the probability will depend on the background information. And this is the crucial thing. Excuse me. It's the crucial thing that comes in, as you know, in Bayes' theorem, the prior information. Cox then found out what is the best way to make an inference by imposing essentially a consistency requirement. We cannot allow two different methods of computing that probability to give two different results, because then we wouldn't know anything, you know, if there are many results possible. So we have to require consistency, which means if I have two or more ways of calculating this probability, then the results have to be the same. This consistency requirement, he used using Boolean logic, essentially algebra. And then he found that this consistency requirement led to functional equations, the solutions of which prove that there is only one unique way of making this best inference from the data, and that is the rules of probability theory. He found that ordinary probability theory has these rules. For x and y, any two propositions, since it's a binary thing, x, proposition x is either true or false, obviously the sum rule has to be satisfied. And this is the product rule for the joint conditional probability distribution for x and y to be true at the same time. Those are the ordinary rule of probability theory. We found that the consistency requirement in making plausible inferences required exactly the same rules. So probability theory now becomes the logic of science, and that's what one of the great proponents of Bayesian analysis, you will know, Edwin James, has written a book with the collaboration of Larry Bradhurst called Probability Theory, the Logic of Science. Now, I haven't listed that down because probably you're all familiar with it, but it's heavier reading than Seeley and Skilling's book. So if you are a beginner, you better start from Seeley and Skilling and then move on to James' book. Anyhow, the important thing is that all these probabilities are written as conditional probabilities. And the reason is very simple. There are no absolute probabilities, no matter what the frequentists say. Because as I said with the example of will it rain this afternoon, everything depends on the background information. So this I after the bar, which is the background information, is crucial. And that was the point where the frequentists attacked us, because they said, you have to state the prior probability that x is true. Meaning, what is your knowledge before you actually see the data? What is your knowledge of the phenomenon, of whether that is true or not? And I said, that's subjective, while our deduction, logical deductions, are objective. If you have a frequentist definition of probability, that frequency is actually something measurable. I don't know how, because you need an infinite number of data, but there is a belief in the frequentists that if you have enough data, then you don't have to go to the limit. You can take that as the frequency. But that, of course, is as subjective as, you know, how many times you flip the coin before you accept the probability of a fair coin to be 1/2. These sum and product rules are essentially the two fundamental mathematical equations from which most of other probability statements can be derived. In particular, you can derive Bayes' theorem directly from that. And the way to do it is to notice that the joint conditional probability of two proposition x and y to be true can also be written as probability of y comma x, because probability of x and y to be true, or probability of y and x to be true, must be equal. So if you do that and rewrite it that way, then you have these two statements. The left-hand side has to be equal because, as I said, the joint probability doesn't depend on the order of x and y. So the right-hand side must be equal. Equate the right-hand side, and you get Bayes' theorem. And you can derive lots of other things, which I won't bother to go through. Anyhow, the way this is true for any two propositions X and Y. The truth as a statement about the truth of the two propositions. But in applying this to science, as the book by Sylvia Skilling points out, you can see much better what that means if you replace X by hypothesis and Y by data. Then the left-hand side gives you the probability that the hypothesis is true based on the data and the prior information, and that's proportional to the data that you've got, which essentially the probability of the data given the hypothesis and the background information, times the probability that the hypothesis is true based on your background knowledge that you have assigned a probability there. The technical names you know very well, posterior, likelihood, and prior. And I wrote proportional because in many cases, and I'm limiting myself to parameter estimation, hypothesis testing type of thing, the denominator is actually nothing but a normalization constant. But for instance, in model selection, you better take care of that thing. I have an example of a medical diagnostic test later on to show you that that is actually comes in, and you can't write any proportion. Let's look at a simple example of how this works. And I've taken the usual flipping of coins. There is this beautiful example in Sylvia's book. And so let's see what happens if we look at this simple case, which cannot be treated by the frequencies because there aren't enough data to define a frequency. So suppose you have, say, flipped the coin 16 times, and you got 6 heads. And then you ask, is the coin fair? Since you can't define a frequency based on those data, the frequentist approach doesn't apply. But we can apply Bayes' theorem and make conclusions. So let's see what happens. How do we do that? Well, the simplest way is to introduce a parameter that represents the biased, say, either for heads or for tail. I took bias for heads. So I took the little h, a number between 0 and 1, meaning 0. If h turns out to be 0, then that means we get tails every time we flip the coin. And if we get 1, it's heads every flip. And you know, the truth will be somewhere in between because we didn't get all heads or all tails. So then what we can do, we can subdivide this interval 0, 1 into a large number of subintervals, as many as you want. And then essentially we can treat this as hypothesis 1, 2, 3, etc. that h will be between these two values, these two values, these two values, and so on. We calculate the probability distribution for that h, and we get a curve. So remember that in Bayes' theorem we need the prior probability given the background information. So before we start the experiment, before we look at the data, we have to assign the prior probability, which comes from background information. After that, we get some data, and therefore we have the likelihood function. Then we apply Bayes' theorem, and we get the probability that we want, the posterior probability. Well, in Sylvia's book, there is a series of graphs for the simulation he did, so I didn't redo the simulation, and I just show you what happens. So, prior information, assume we don't know anything about it, and so we have complete ignorance. That means we have to assign a probability, a uniform probability for the prior. So let's say we just assign 1. And how do we calculate then the likelihood function? Well, when you flip the coin, it's a binary type of possibility, either heads or tails, so we can use the binomial distribution, which I just put there. I remind you, it's just h to the r, 1 minus h to the n minus r, n is the number, and r is the positive number of heads coming out. So when we do the first flip, in the first flip we get a head. So then in this case, because I've taken the prior to be 1, then the likelihood and the posterior would be essentially proportional to each other. So we get a straight line. Well, even if we stop there, we could make a meaningful statement. We don't know the truth, but it's still possible to use Bayes' theorem to make a statement there. For instance, if I had just that, I would say, well, chances are good that it's a two-headed coin. And if I do twice and I get another head, I can say, well, now it looks as though actually we have a two-headed coin, right? It's not necessarily the truth. If you calculate the error over there, it's huge. So you can't trust that conclusion. But the conclusion itself, that it looks as though after two flips, you are dealing with a two-headed coin, is not stupid by itself. It's just that you can't trust it because the error is too big. In fact, if you do it another time, now you know that it's not two-headed because it goes down to 0 when h is equal to 1, right? But you see, you start to get a curve, and now you can say, well, the likelihood, the chance that, you could think of taking the maximum here as a rough estimate. And you say, well, it seems biased towards head. But the error would be something like the spread here, the width at half height, and although it's not symmetric, it's quite obvious that it's huge. So you can't really trust it very much. So keep repeating. And by the time you reach 16, you see actually now that the posterior probability starts to go towards tails, bias towards tails, you see, is left of 0.5. And so if you had 6 heads on 16 trials, you had 6 heads, the posterior tells you that it's likely to be biased towards tails. You still have a big error because the width of the probability distribution is large. But if you keep going, the more you flip the coin, of course, the more the data pile up and the better it is. And finally, when you've done it 4,000 times, it's quite clear that it's around 0.25, and it's very clear that bias is towards the tail, right? You might ask, well, I started out with complete ignorance as my prior. What if I change my prior? Well, the probability distribution will change, of course, Bayes' theorem that multiplies the likelihood function. And if you redo that with different priors, actually, in this case, there are 3. For reference, we put in also the blue is actually the previous one, uniform ignorance. Then we put in this probability distribution, which is centered, which is peaked around all tails or all heads, which is the worst possible type of prior distribution you can have. And then you can say, well, reasonably, it could be a fair coin, so let's take a sort of symmetric distribution around 0.5. Now, run the experiment and use Bayes' theorem and see what the probability distribution for the posterior does. Well, first, again, repeat heads the first time, heads the second time, and so on. You see that for the uniform distribution, we get what we got before. But the the other 2 prior do not change very much when you have very few data. If you increase the number of data, then of course the thing will start moving. And by the time, say, you reach 15 trials, now you see that both the uniform prior and the extreme prior of peaked around 0 and 1 start to get coalesced together. Yep. The other one still insist that it's a fair coin. And if you keep repeating it, you will find the interesting thing that if you start with a fair coin, it will take many more data before the dashed line is the assumption of fair coin, before you can get convinced that actually it's not a fair coin. You see how many, more than 1,000 before you bring the assumption of the fair coin distribution to the actual distribution. It takes much more data. If you start with a prior that says, I know this, then you need a lot of data in order to convince you that it's not true, that the posterior is changed. Well, the beauty of this, with this simple example of the fair coin, actually applies also to clinical trials, for example. So if you do, I took this from a paper by Donald Berry. Suppose you do a clinical trial and you call S success, say, for the drug that you're testing, and F failure. And suppose you have a sample of just 10 results. Success, success, fails, success, success, fail, and so on. And then you repeat, essentially, it's again a binary type of thing, so it's exactly the same as the example of flipping the coin with the binomial distribution, and you get this. You get that the posterior now tends to go, say, in this case, the parameter, what I called H before, is actually a question of success or fail. And so the probability peaks around a certain value, say 0.7, 70% probability for the maximum. And the error is still quite big. But you can stop at any time and still make a sensible, plausible statement about the future. Another example of application of Bayes' theorem is on something that we are all familiar with from press and the media in general, and that is diagnostic tests. There are so many diagnostic tests that people usually are very confused about it. So suppose I just want to illustrate what a diagnostic test is that it's like a case that you have a new disease and the pharmaceutical lab develops a test to spot whether a patient has the disease or not. Usually the test is defined by giving two numbers. One is called the sensitivity and one the specificity. Medical people like names, and what precisely those mean, I don't know how much they understand it, but sensitivity is actually the probability that if you have the disease, the basic information, the background information is always there. I won't talk about it, but that's the important thing that you have to consider. Take the probability that a group of patients that has the disease takes the test, and the test comes out positive. So if for a group of patients that all have the disease, the test is positive, that's called the sensitivity. So that 95% means essentially that if you have these people with disease and you apply the test to them, 95% of the time it will give you a positive result. Specificity, instead, is in those people that do not have the disease, the test should give a negative result, right? To be a good test. Well, in this case, it shows that the probability that the test is negative if you don't have the disease is only 80%, which means 20% of the time the test may be wrong. You may not have the disease and it gives a positive result. Okay? So now, suppose that a certain person, Mr. A, has no reason to believe that he's got this new disease, but decides to take the test to feel good, to sort of have no problem. And it comes out positive. Does he have the disease? What's the probability that he actually has the disease, given these characteristics of the test? Well, if you are an ordinary person with no understanding of Bayes' theorem, you might think, man, it's positive and the sensitivity is 95%. I've got 95% chances of having the disease, right? That would be sort of natural for the person to get scared of. Well, let's see what Bayes' theorem tells us. So we set up Bayes' theorem by defining things. So let's define the symbol DIS says the patient has the disease. The negation of that with the over bar means not to have the disease. Plus means the test is positive. Now, the sensitivity, as I said before, oh, I'm sorry, instead of 95, I put 98. I put 98. I put 95 if you want to redo the calculation. That's the sensitivity, the probability that if you have the disease, the test will be positive. Now, in Bayes' theorem, we don't need the specificity, the probability that if you don't have the disease, you will get a negative result. Because what we will need is the probability that if you don't have the disease, you get a positive result. That's what you are interested in. And then, of course, we call the incidence rate the prior, because we only know that the disease appears in 1 of 100 people in the population. Then apply Bayes' theorem to the calculation, and I did it with 98 rather than 95, so the change is very little. And you get 0.0447 for the probability that if the test is positive, you've got the disease, the posterior. So you have about 5% chance of having the disease with the test coming out positive. That's very comforting for the patient, right? But very few people understand and appreciate that. And so I hope that the Bayesian approach will spread with the medical people and remove some of the trouble, trial, and panic situation that people feel when they get all these tests, and especially since these tests have usually high sensitivity maybe, but very, very low specificity, which means if you don't have the disease, the test can still come out positive, and that produces a lot of anxiety in people. So I hope that the future will be more Bayesian in the medical area, but don't hold it back, because it's pretty difficult to eradicate this kind of symbol. Thank you very much. You are saying time? Yeah.
Yes, you were very good. Thank you very much. I think we do have time for questions, and with a comment as well.
Yeah.
There is an International Society for Bayesian Analysis, which is a collection of statisticians that has 10 times our numbers and 50 times our resources. They're very proud of themselves for having seen off the frequentists, even though they still have large numbers. I'm got involved with this organization, but I'm rather wary, because although they've won a battle, it's my sad belief they haven't yet won the war.
Yeah.
They've defeated smallpox, but they're still drowning in potion. This is unfortunate.
Yeah.
I seriously think that in this meeting here, we're a generation ahead of all this. We really are out ahead, leading. And it really all comes back to Richard Cox and all that stuff we started with.
Especially since there are empirical Bayesians, statistical Bayesians, all sorts of people that claim to be Bayesian, but they're not Bayesian.
We're the fundamentals.
Yes.
Okay, questions? Yes, one over there.
Yeah, you mentioned focused on sort of medical applications, which seem a very obvious area. But do you have a sense of whether, discipline-wise, there are other fields that are sort of early adopters? And you mentioned the past. I mean, is Bayesian analysis used a lot in electrical engineering or astronomy?
Yeah. One of the most successful areas where Bayesian analysis has taken over is actually in areas like econometrics. And I'm sad to say, as a physicist, that not many physicists have embraced the Bayesian analysis yet. In fact, I just read a few months ago a paper saying why not most physicists are Bayesian, why most physicists are not Bayesian. And there is, I think the main reason why physicists sort of do not want to jump in is because of quantum mechanics. See, one of the reasons I became a Bayesian is I could never make heads or tails of quantum mechanics, and we'll hear more about it in future talks. But I just studied, when I was in graduate school at the University of Toronto, I took 4 advanced courses in quantum mechanics, and I couldn't make heads or tails. So I went to my supervisor and I said, please help me, what does this mean? And he said, Mr. Tenti, I'm one of the school, shut up and calculate. I suggest you do the same if you want your PhD. So, you know, then finally when I got to my own, I said, well, enough of this, I went Bayesian. But a lot of people believe that quantum mechanics is correct as it is. And therefore, there is no need to change the interpretation of probability in quantum mechanics. I mean, if you think about it, there is some work done by Professor Luke and Katish, I think, as well, is talking about it, about the meaning of probability in quantum mechanics. It's a very complicated program. Why should the modular square of the wave function be the probability in our sense? They are dealing with amplitudes which are complex numbers. And so interference problems and so on are always dealing with complex numbers. And that thing has to be resolved before actually people in physics will sort of stop talking nonsense. I'm a bit brutal, but but we agree.
No, that's a question. If we fix that one.
When you were discussing the sum product rule,
yeah,
and you emphasized conditioning on background information, I would think this would be the one case in probability theory where you could dispense with the background information, because those rules, those formal manipulation rules, like the sum rule, the product rule, the Bayes theorem,
yeah,
are true whatever the background information might be. So,
yeah, I agree. The rule is valid anyhow, but the question is the role played by that probability of y being true based on the information is that the background information is so crucial in the interpretation of Bayes' theorem as giving you the probability for a correct inference. Keep in mind that if you use the Kolmogorov definition of probability, the rules are still the same, but they still interpret the probability as frequency.
Right, well, you definitely need background information if you're going to make a numerical assignment by a maximum entropy principle. But I'm just saying that you could certainly dispense with background information when you're saying the probability of X and probability of
No, the rules, I agree. The rules are valid anyhow, but the question is that probability of y given I is interpreted as frequency by the standard frequencies, and is interpreted by us differently because of the different point of view. But the rules, yeah, the rules are the rules of probability.
I just want to be a little bit more specific about your response. If there are strongholds of Bayesian probability in physics, I think in many areas Bayesian probability theory is now very common, especially astrophysics. There is one stronghold which is severely rejecting Bayesian inference, that's high energy particle physics. So you have a pretty tough time at CERN, the LHC, but otherwise in many other areas it's pretty common, and especially if you do a lot of model comparison, because there the frequency.
You are right. Astrophysics is actually the area of physics where most Bayesians have gone ahead using the Bayesian approach. I was more concerned with quantum mechanics.
I think one of your very early slides sort of alluded to one of the biggest problems in getting people to adopt Bayesianism. The slide you sort of showed us for a bit of comedy, where you had all the different things that could cause cancer. In a world where people have got to come up with some sort of result to keep their careers going, isn't it always tempting to just say, this is 95%, this is 95%, test the correlation between 20 different things and find a result? I mean, what would you say is the best way to counter that incentive?
Well, so far as I know, the MD Anderson Cancer Institute in Houston has done the most work in trying to convince the Food and Drug Administration to actually accept Bayesian clinical trials to approve drugs. So far as I know, they've done only one approval with the Bayesian approach, but there is hope that the more people in areas like Donald Berry and Stephen Goodman are propagating these ideas among the doctors, that we will end up one day actually making clinical trials interpreted Bayesian, which would be much more sensible and, above all, more ethical. Because, as I said, if you have a case where the time of the clinical trial has to be fixed, and you discover that the drug is effective after a very short time, it's sort of unconscionable to keep killing people because they can't get the drug since they are in the control group. So I'm more optimistic about it. The only obstacle we really have is that the statisticians that work with medical people are ingrained frequentists. Most of them just use the software without knowing what they're doing. The doctors are so afraid of mathematics that it's very difficult to interact with them. So it takes some time and patience.
What is your experience when there is a situation when bias changes over time? For example, a coin is not a rigid body. What is your experience? How do you take into account this effect?
The change in the background information?
No, bias changes. A coin, for example, cancer might be...
Oh, changes in the data themselves.
Yes.
Well, but the beauty of Bayes' theorem is that you can actually use it successively, sequentially. So if I start out, say, with complete ignorance for my prior, and then I get a bunch of data and calculate the posterior, as new data come in with different results, I can use that previous posterior as the prior for the next application of Bayes' theorem. So it is actually, Bayes' theorem is actually the process of learning in science. The more new data come in, the more I learn. And I can reapply and change my opinion and the plausibility of my conclusion depending on new data. That's how science works, really. And Bayes captured that. It's the method of learning.
We can get more and more sophisticated as our information. Question there,
I want to ask a question. I come from engineering, and the application of Bayes' theorem are absolutely, there's no contradiction using Bayes' theorem or Bayes' theory, for example, communication theory.
Yeah.
Communication theory is strong, it's practically strong depend on Bayes' theory. So I'm totally with you on this. What I see in the engineering context as a real innovation of dealing with the type of problems that you were pointing out before is the possibility of putting together problems of data with problems of logic. And because these two worlds express, at least they have expressed it as strongly different approaches. And the real chance of these ideas is to put them together. I must say that I wanted to get your comments on this because the implication of Bayes' ideas are strongly related to the idea to our capability of dealing with uncertainties about the model. And there are lots of people thinking about alternative theories of probability, but essentially the problem is how to deal with uncertainties.
Yep.
Not because Bayes' theory is not right, but because we don't know enough about the problem with the model.
Well, I hope that people will converge to understanding that once you get the probability, the posterior probability, some people just, if you have a symmetric distribution, it's a good approximation to take the maximum as best and the width of the probability distribution as the square of the error. So you take the square root of that width and you have the sigma. But as Professor Skilling pointed out in the paper that I quoted, choosing the peak of a probability distribution is an approximation. He uses the example of a mountain. If that were the shape of a mountain, you may have a peak which is very high and very sharp. But what you are supposed to do with Bayes' theorem is explore the entire summit to find out what the probability tells you. I think these are subtler type of things that haven't percolated yet into the entire scientific. But there is hope. maybe these meetings are the ones that, as John was saying.
One comment, you correctly said that there is no absolute probability. I just want to comment that the statement there is no absolute probability is also used in slightly different context in some mathematical, in some books of probability, like and that's that there is no absolute probability. Every probability is given that omega, that you have done experiment, that you will do experiment, that one of the events has occurred or will occur in a different sense. Otherwise, there is no absolute probability. If you don't roll the die or whatever,
there is a second problem that in most of the ordinary frequentist interpretation, when they see a conditional probability applied to a physical case, they interpret the condition as the cause of the result.
That's right.
And Ed James has pointed out very clearly that it's a logical inference, not a physical.
It's conditions that given omega. That the certain event occurred. I mean, one of the.
Just two quick comments. First, just to play devil's advocate, the one thing about traditional statistics is it's cheap, right? But as I say, you get what you pay for. So, and the cost of base is coming down every day. They come out with a new computer chip. So, but the other thing is you mentioned MD Anderson. So I was actually at MD Anderson talking to Don Berry, and one of the other people I talked to there was from the FDA. So this came up about patients, and the people that are in charge at the FDA are predominantly patient. But here's the problem, and this is the practical problem, is that they can't decide on a prior. Company A says they have a prior that they want to use, and it's the correct prior. Company B says they have the correct prior. And since the FDA can't decide on whose prior they should use, so they don't want to show any preferential treatment,
unless they have the p-value.
They use a uniform prior, and so they're right back to the traditional statistics. So, and since the FDA will only accept uniform priors, anybody who's publishing doesn't want to use Bayesian statistics, so their trials aren't going to be accepted. So this is a real issue that needs to be resolved.
I hope they succeed, because otherwise we get all.
Anybody here can contribute to that.
No, I think the next contribution really ought to be coffee. Sorry about that. This could go on for a very long time. Let's thank our speaker.